Hello, ladies and gentlemen. We're going to do section 3.1, extrema. Now, the word extrema means that. Exactly. It means the extreme cases on a function. For instance, the highest and the lowest. In this case, an intuitive sense of what extrema are the highs or the hills, or the lows, the valleys. Let's consider this graph right here. Just looking at it, intuitively, you should be able to look at this and say, Mr. Martinez, this point right here is the lowest point on the graph. That's my low extrema, what we're going to call a minimum. And here, this is the very top point. This is my maximum point, or the highest point. If you have that intuitive sense of a maximum and minimum, then you're on your way of understanding what it is to mean, what it means to be an extremum. Let's look at it from a different perspective. Let's look at it at the calculus perspective. We got to consider the interval on which the graph exists. For instance, f of c, which is a y value at c, f of c is a minimum if f of c is less than or equal to f of x for all the x in that interval. What does that mean? It means if I have some c value here at c, this y value, or f at c, if it is the smallest value on this function, then it is called the minimum value. Okay? Now, let's look at the definition of a maximum. The definition of a maximum, and please excuse this word type, says f of c is a maximum if f of c is greater than or equal to f of x for all x in that interval. Well, this value up here, this y value for this particular c, is the highest y value on this interval that this function is defined on. Okay, so that's kind of the definition of extrema. Let's look at some examples, some other examples. Consider this. It has open dots at either end. Here, this still has a minimum value, so we can call this the minimum because it is the smallest y value on this entire interval. But the highest point is non-existent. So this is not a maximum because there is no point that is the absolute greatest value. You could get close and close to this open dot and never actually touch it. So there is no maximum. Let's look at this case. In this case, there is no minimum value. That point has been redefined up here to this f at c. Okay? So at c, this is the new value. There is no lowest point, so there is no minimum. Right? But this value up here is a maximum value because on this interval for which the function is defined, this is the highest y value. And again, it still goes with the intuition of what is the biggest and what is the smallest, but we have to consider sometimes those points don't exist. Okay? Now, ladies and gentlemen, we're going to look at a theorem called the extreme value theorem. An extreme value theorem states if f is continuous on a closed interval a to b, then f has both a minimum and a maximum value. A closed interval, ladies and gentlemen, is an interval on which the function is continuous. You can draw it without lifting your pencil, and it does include the endpoints. If it is continuous on a closed interval, then you're guaranteed to have both a minimum and maximum value. These values are sometimes referred to as absolute extrema, or absolute maximum, absolute minimum values. Oh, and by the way, this extreme value theorem is an existence theorem. It tells you it exists, it just doesn't tell you how to find them. Kind of like aliens. I could tell you they exist, I just don't know where they're at. All right. Let's move to relative extrema. Well, what's a relative extrema? A relative extrema can be found on an open interval, okay? And that open interval contains some c value, and the f at c is a maximum. If it's the maximum value on this open interval, then it is called a relative maximum. Okay? Now, open intervals don't necessarily include the endpoints. Sometimes the endpoints are non-existent. Sometimes they just go on forever. Okay? They're infinite. And we'll talk about this in a second. An open interval containing c and f of c is the minimum value, then it is called a relative minimum. Again, when we talk about relative minimums, relative maximums, absolute minimums, and absolute maximums, the big difference is absolute extrema occur on a closed interval, and relative minimums exist on open intervals. For the most part, that's how you can distinguish them. Now for critical numbers. Ladies and gentlemen, when we start talking about extreme values on a function, we need to consider all critical numbers. So there are different forms and different types of critical numbers. A critical number is defined as a value in the interval at which the derivative is 0 or undefined. So think about that. If you have a 0 for a derivative, you have a horizontal tangent. This is going to be one of your critical numbers. Doesn't mean it's an extrema. It just means, hey, we need to consider this and see what's happening at this critical number. Also, we could have a sharp point, which would mean our derivative is undefined. At these points, we could also have extrema. Okay? So these are just numbers we need to, critical numbers are numbers we need to consider for extrema. Also, on a closed interval, the endpoints are critical numbers. You see, when you have a closed interval, you have endpoints, and you have to consider, are those the highest or the lowest values? Are they maximum extrema? Are they minimum extrema? So critical numbers are any places where extrema could exist. And one way you can tell is that if they're endpoints, or if the derivative at those points is 0 or undefined.